Okay, video of me going through the March mocks for Year 13, 2022. Okay, this is Core Pure Paper 2, so this is further maths. And it's going to do the whole paper. So, question number 1. Given that Z1 is this complex number, okay, given in modulus argument form, and Z2 is this complex number, write down the exact value of modulus of Z1, Z2, and the argument of Z1, Z2. Okay, so for part A, part I, the modulus of the product of two complex numbers is equal to the product of the moduli. Okay, that's something you need to know. So that is going to be 3 times the square root of 2. So that's just 3 root 2. Okay. Part 2. The argument of the product. The argument of the product of two complex numbers, Z1, Z2, is equal to the sum of the arguments, Z1 plus the argument of Z2. Again, that's another fact you just need to know. The argument of the first complex number is pi on 3. And the argument of the second complex number looks like pi on 12, but just be careful because there's a minus sign there, which means that should really be a positive, and then a minus should be put into both of those. So now we can read off the argument, and it's actually minus pi on 12. So just be careful there. It's got to be of the form cos of theta plus I sine of theta inside of that bracket. Okay, good. So we've got pi on 3 minus pi on 12. Well, that's 4 pi on 12 minus pi on 12 is 3 pi on 12, which is pi on 4. There we go. If you just wrote the answers, that's fine, full marks, because it's just 1 mark for each. Okay, given that W is the product of Z1, Z2, and that the argument of W to the power n is 0, where n is a positive integer, determine the smallest positive value of n and the corresponding value of the modulus of W to the n. Okay, so for part B, well, the argument of W to the n is going to equal n times the argument of W. Again, that's a fact you need to know when you're raising complex numbers to powers. And we want this to equal 0 or any multiple of 2 pi. So 2 pi, 4 pi, 6 pi, etc. So for each multiple of pi, you're spinning around the origin once. So the smallest is obviously when n is 0, but we don't want 0 because we're told that n is a positive integer, which means we need n times pi on 4 to be 2 pi. So we get n times pi on 4 equals 2 pi. The pi's cancel, times the 4, we'll get that n is 8. Okay, so n is 8, that's the smallest. And if you think about the Argand diagram and what's going on here, then we've got W, which is over here, which has an argument of pi on 4. If we want to raise that to integer powers, and when we square it, it'll be pi on 2. Cube it, it'll be 3 pi on 4. Raised to the power 4, it's going to be pi. Keep going. 5 pi on 4. 3 pi on 2. 7 pi on 4. 2 pi. And that is 1, 2, 3, 4, 5, 6, 7, 8. Okay, we want to get it around to the real axis. So n is 8. Part 2, find the corresponding value of the modulus of W to the n. Well, the modulus of W to the n is going to equal the modulus of W to the power n. Okay, again, that's another fact you need to know when raising complex numbers to powers. We've already calculated the modulus of W. That's 3 root 2. And we've also already calculated n, which was 8. So I just need to do 3 root 2 to the power 8. So I'm going to get my calculator. 3 root 2 to the power 8. You get 104,976. 104,976. That's my answer. question 2. Matrix A is given as that. The matrix A represents a linear transformation M. Prove that for the linear transformation M, there are no invariant lines. Okay, so the invariant line is a line that maps to itself. So what we're going to do is 4, -2, 5, and 3. Take a line. I'm going to take a line through the origin. Because if there are invariant lines, then it will be plus c's of those, like for example in a reflection perhaps. And I'm going to say that y equals mx, so it's just some line through the origin, and that's going to map to some multiple of that. So I'm going to call it lambda times mx. So this line then, any point x mx has mapped to some other point which has x mx, so it's got the same gradient, but a different point on the line depending on what lambda is. And my job is just to show that there's no values of m for which this is true. So carry out the matrix multiplication. I get 4x minus 2mx equals lambda x, and then the bottom line I get 5x plus 3mx equals lambda mx. Okay, if I eliminate lambda from those, I'll get 5x plus 3mx equals lambda, but lambda is this right hand side divided by x, so that's 4x minus 2mx divided by x times mx. Okay, so that's what we get there. And the x's will cancel. Now we're going to get 5x plus 3mx minus 4mx, so that's just minus mx. And then I've got a plus 2m squared x. That's going to equal 0. Divide by x. Okay, the x's will cancel, so I get 5 minus m plus 2m squared equals 0. And I can divide by x because we know that x equals 0, y equals 0 will be an invariant point, because that's always invariant in a two-dimensional transformation with matrices. So we can ignore that x is 0 as a solution. So we end up with this quadratic. So what value of m is true? So we end up with m is equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a, which is not real, okay, because we're going to try and square root negative 39. Okay, the square root of minus 39 is not in the set of real numbers. So there's no real value of m for which this is true, therefore there's no invariant lines. Okay. If you wanted to be a little bit more general and take any line, then we could use the matrix times x and then mx plus c, so that would be y equals mx plus c, so that's any linear line, and we want that to equal lambda x, and then again y equals mx, so lambda mx plus c. And if you followed that algebra through, then you get to the same result. But you also have the extra thing with c kicking around. You end up with, I'm trying to remember off the top of my head now, something like 3c equals minus 2mc plus c or something like that. In which case c is 0, like the result we've just found, or m is minus 1. But that doesn't fit with the quadratic, so it doesn't matter. That isn't a solution. So, yeah, so this is fine. You don't have to do the plus c. You can stick with that. Okay, that is sufficient. Okay. Question 3. Using a substitution that should be stated clearly, show that the integral of this function is a constant times the inverse sine of b times x plus c, where c is an arbitrary constant, and a and b are constants to be found. Okay, so we have this function here. We're going to integrate. Okay, so my initial instinct is to try and make that denominator u squared plus 1. So I'm going to say 4x squared plus 9 equals u squared plus 1. That's the substitution I'm ultimately going to try and get to. So what I'm going to do is I'm going to pull out 4/9 from that. So the integral of 4 times the square root of x squared plus 9/4, all under 1 dx. The square root of 4 can now just come out of the integral as a half. No, I've done it wrong. Start that again. I want to pull out a 9th because I want to make this a 1. Apologies. So we're going to get the square root of 9 times the square root of 4 over 9 x squared plus 1, all under 1 dx. There we go. Now we pull out a third, and we get the integral of the square root of 4/9 x squared plus 1, all under 1 dx. And now I can make my substitution. I want this to be a u squared, so I'm going to say that 4x squared equals 9u squared. And if I square root that, I'll get 2x equals 3u. So that is a substitution I am making, and that has been clearly stated as the question has requested. So I'll get then that dx by du is equal to 3/2, which allows me to make this substitution. So I'm going to get that the integral is a third times the integral of, well, because of how I've chosen this, that will be u squared, okay, because 4 over 9x squared is just u squared. So that's the square root of u squared plus 1 divided by 1 times dx, but dx is 3/2 du. We end up with that. And the 3 to cancel, and I get a half there, and I get the integral of the square root of u squared plus 1 under 1 du. Okay, now checking the formula book. This integral is given in the formula book as just the r shine of u, so we end up with a half times the inverse shine, which I'm going to write as r shine of u, and then plus my arbitrary constant, and then take my definition of u up here, which is 2x on 3, and plug it back in. So I end up with a half times r shine of 2x on 3 plus c. Okay, so that is my answer. Just check that it makes sense with what is given. So it's a constant times the inverse shine of b times x. Great. So my first constant is capital A is a half, and my second constant is capital B is 2/3, and that fits with what it says it should be. So that was part A. Part B. Hence find an exact form in terms of natural logarithms, the mean value of f of x over the interval from 0 to 3. Okay, so for part B, by the mean value theorem, is going to be equal to 1 over 3 minus 0 times the integral from 0 to 3 of f of x dx. Okay, so that's the mean value theorem. I'm finding the mean value from 0 to 3, so I need to take that integral and divide it by the x difference, which is 3. So that is going to be a third multiplied by, and then this integral, which I've just calculated, is a half r shine of 2x on 3. That's a half r shine of 2x over 3, and that is between 0 and 3. The plus c cancels with itself, so you don't need to include it for this definite integral. So that's going to be a sixth r shine of 2. Okay, plug in x is 3. I'll cancel, and then plug in x is 0, you get minus 0. It says it wants it in terms of natural logs, so I need to have a look at what that is in the formula book. So if I jump to the formula book, apologies, just to bring it up on here. There it is. So that is going to be a 1/6 times the natural log of, that's AS further maths, scrolling down to A-level math, A-level further maths, just there. Okay, and I want the logarithmic definition of R shine. Should be in the hyperbolic section. There it is. It is the natural log of x, which is the content of the R shine, so that's 2, plus the square root of x squared plus 1. Okay, so that was taken directly from the formula book, which is a 1/6 times the natural log of 2 plus root 5. And that's my answer. Always worth checking these things. So on my calculator, I'm going to integrate up here. So that is 1 over the square root of, it was 4x squared plus 9. From x is 0 to 3. I need to times that by a third. Okay, so that's my mean value calculation. And I'm going to subtract my answer, and that should be 0. So minus a 1/6 times the natural log of 2 plus the square root of 5. That should be 0, which it is. So that confirms that that answer is correct. Question 4. The plane pi1 has equation r equals this thing, which is in parametric form. So we've got some point on the plane plus lambda times some direction on the plane plus mu times some non-parallel direction to that one on the plane. So we've got 2 non-parallel directions on the plane, where lambda and mu are scalar parameters. Find a Cartesian equation for pi1. Okay, so what this represents is it represents 5 equations in 3 equations in 5 unknowns. So the unknowns we've got are x, y, and z from the left-hand side here, and then lambda and mu as our parameters. And to get the Cartesian equation of the plane, I need to eliminate my 2 parameters, lambda and mu. So what I'm going to do is going to extract all of these equations. So x is 2 plus lambda minus mu. Okay, so 2 plus lambda minus mu. So I'm just looking at the I direction. The j direction, y on the left is 4 plus 2 lambda plus 2 mu. And then my z direction, I get z is equal to minus 1 minus 3 lambda plus mu. Okay, so those are my 3 equations. And I'm going to call them 1, 2, and 3. Okay, right, let's eliminate one of those parameters. Let's eliminate mu first, just because I've got a mu kicking around over there. So to get rid of mu, I'm going to first of all calculate equation 2 plus 2 times equation 1. Okay, so if I do that plus 2 times that, the mu's will cancel. So equation 2 plus 2 times equation 1. So the left-hand side will be that. Equation 2 plus 2 times equation 1. Equation 2 plus 2 times equation 1. I get y plus 2x equals 8 plus 4 lambda. And now if I do 1 and 3, and just add those together, then again my mu's will cancel. So I get x plus z equals 1 minus 2 lambda. Okay, so I'm going to call that equation 4 and equation 5. And now I eliminate lambda from those two. So if I do equation 4 plus 2 times equation 5, so equation 4 plus 2 times equation 5, that'll get rid of my lambdas. So I'll get my x's, I'll get 4x. My y's, just the one y. And my z's, I'll get plus 2 z's. And that's going to equal 8 plus 2, which is 10. And then the lambdas cancel. And that is the Cartesian equation of the plane. Done. Okay, so that's my answer. All right, the line L has this equation. Find the coordinates of the point of intersection of L with pi 1. Okay, so this represents a line, and I'm going to solve them simultaneously. So part B, I'm just going to write x, y, and z of the line in vector form. So I'm going to say x, y, z is equal to some point on the line, which is the negative of the tops, so 1, 3, and minus 2. Okay, so when x is 1, y is 3, z is minus 2, that satisfies the equation because all the tops will be 0. Plus some parameter. Now lambda and mu are both taken, so I need another one, so let's call it alpha, doesn't really matter. Times the direction, which is the denominator. So I've got 5 minus 3, 4. Okay, so this says that x is equal to 1 plus 5 alpha, y is equal to 3 minus 3 alpha, and z is equal to minus 2 plus 4 alpha. And if I take those three definitions there and plug them into the equation of the plane, I'll get a linear equation in alpha to solve, and then I plug them back into here, and that will give me the coordinates of intersection. Okay, so I've got 4x, so I get 4 plus 20 alpha, plus y, so that's plus 3 plus minus 3 alpha, and then plus 2z, so that's minus 4 plus 8 alpha, and that should equal 10. Those two cancel, so I get 7 on the right, and I've got 20 alpha plus 8 alpha minus 3 alpha, so I get 25 alpha on the left. So I get that alpha is 7 over 25, and then that gives me my point over here. So if I do 1 plus 5 times 7 25ths, that gives me my x coordinate to 2.4. My y coordinate is going to be 3 minus 3 times 7 25ths, which is 2.16. And then my z coordinate is minus 2 plus 4 times 7 25ths, which is minus 0.88. So that is the coordinate of my point of intersection of my line and my plane. And I should probably check that before I finish. So it obviously lies on the line because it fits with these. That's how I got those in the first place for this value of alpha, and just check that it does indeed satisfy the equation of the plane. So 4 times 2.4 plus 2.16 minus 2 times 0.88 should equal 10, and it does. Okay, so those 3 points satisfy the equation of the plane. You can plug them through here as well if you really wanted. So x minus 1 over 5 is 7 25ths. Y minus 3 over minus 3 is 7 25ths. And z, which is minus 0.88 plus 2 over 4 is 7 25ths. Okay, so that point also satisfies the line. And then part C. Find the nearest degree, the acute angle between pi 1 and pi 2, and pi 2 has this equation here. So this is a slightly different form of the equation of a plane. Okay, it's r dot some vector equals a constant, and this vector here is the normal vector to that plane, so I'm going to call that n2. So the angle between two planes is equal to the angle between their two normals. So for part C, the normal to plane 1, normal to pi 1, was the coefficient, so 4, 1, 2. And the normal to plane 2 is this, it's 2 minus 1, 3. And we want to find the angle between those. So theta is going to equal the inverse cosine of the dot product of those two vectors. So that's 8 minus 1 plus 6 divided by the product of their moduli. So the moduli is 16 to the root 21 times root 14. Okay, that will be an acute angle already because the top is negative. So inverse the cosine of 13 divided by the square root of 21 times the square root of 14. That gives me 40.696 or 40.7 degrees. There we go. Question 5. The curve C has this equation, y equals arc cos of a half x, and we're told x lies between -2 and 2 inclusive. Show that it has no stationary points. Okay, so first of all, I'm going to cos both sides. So I get the cosine of y is equal to half x. Differentiate both sides with respect to x. So that's minus sine of y times y primed equals a half. Set y prime to equal 0. This implies minus sine of y equals a half. And why can't that be possible? Oh no, 0. I added them. Minus sine y times 0, it gives 0 on the left equals a half. Well, there's no solutions for 0 equals a half. Therefore, no stationary points on C. There we go, part B. The normal to C at the point where x equals 1 crosses the x-axis at the point A and crosses the y-axis at the point B. Given that O is the origin, show that the area of the triangle OAB is a 54th into p root 3 plus q pi plus r root 3 pi squared, where p, q and r are integers to be determined. Okay, so we first of all need to calculate this normal line. So normal to C at the point where x is 1 crosses the x-axis at A and crosses the y-axis at B. So we're going to need to differentiate, which we've already done. So I'm going to say y primed is minus 1 over 2 sine of y. And I'm interested when x is 1. X equals 1 implies y equals, and I get arc cos of a half. Now I'm using calculus on trig, so I must be in radian mode. So arc cos of a half is pi on 3. So I get that y is pi on 3. So that gives me the gradient. So y primed when x is 1 is equal to minus 1 divided by 2 times the sine of pi on 3. Minus 1 divided by 2 times the sine of pi thirds is minus root 3 on 3. Or if you like, minus 1 on root 3. And that implies that the gradient I want is positive root 3. And that's because I'm concerned about the normal, which has a negative reciprocal gradient. So therefore the equation of my normal is y minus pi on 3 equals m times x minus 1. Now where it crosses the x-axis, that implies y is pi on 3 minus root 3. And where it crosses my y-axis, sorry, my x-axis, implies x equals, I'm going to get minus pi on 3 divided by the square root of 3 plus 1. Which I'm going to write as 1 minus pi over 3 over 9 times root 3. Okay, just check that both of these are positive, just in case one of them is negative. So we get pi over 3 minus the square root of 3. Oh, that is negative. And this one here, we're going to get 1 minus root 3 times pi over 9. That is positive. Okay, so quick little sketch. My point A is over here where it crosses the x-axis. My point B is over here where it crosses my y-axis. So that is going to be the triangle I'm considering, which means the area is going to be the negative of that because I want the actual length, so the positive number, multiplied by that divided by 2. So the area then is the negative of that, which is root 3 minus pi on 3. Root 3 minus pi on 3. Okay, times by a half because it's a triangle. Multiplied by this length here, which is positive. So that's 1 minus root 3 pi on 9. So 1 minus root 3 pi on 9. Okay, so you tidy that up. So that's going to be a half times root 3 minus pi on 3 minus pi on 3 again, plus root 3 pi squared over 27. Okay, pull out a 27th from that. That gives me the 1 over 54, which is good. So I've got 27 root 3 there. Those two combine to give 2 pi on 3, but I've pulled out a 27, so I need to times that by 9. So it's going to be minus 18 pi. And then I've pulled out the 27 from there, so root 3 pi squared. Let's just check back to what the question is asking for the form. Okay, so it's something times root 3 plus something times pi plus something times root 3 pi squared. So that's exactly what I've got. So p is the coefficient of root 3. So p is 27. Q was the coefficient of pi, which is minus 18. And r was the coefficient of root 3 pi squared, which is 1. That's my answer. You don't have to write that. You can leave it like that because it asks for it in that form where p, q, and r are integers. So you don't have to state p, q, and r explicitly. But it is nice to do so. Okay, I think that finishes question 5. Yes. All right, question 6. The curve C has this equation. So polar coordinates. A and P are positive constants, and we're told that P is greater than 2. There are exactly 4 points on C where the tangent is perpendicular to the initial line, and show that the range of possible values of P is between 2 and 4 strictly. Okay, so part A, perpendicular to the initial line, that's the initial line. So perpendicular would be vertically upwards. The initial line has equation theta equals 0, just in case you weren't sure. So we're essentially looking for when dy by dx is infinite. Now, in terms of kind of parametric definitions or polar definitions, dy by d theta divided by dx by d theta gives you dy by dx. And for this to be infinite, we need dx by d theta to be 0. So dx by d theta must equal 0. That's what we're looking for when we're looking for lines that are perpendicular to the initial line. Okay, dx by d theta is 0. Essentially, as theta varies, x isn't changing at that point. Okay, so you get a vertical tangent. Okay, well, let's just think about what x is. By definition, x is r times the cosine of theta. Okay, definition of polar coordinates. R were given in the question. Okay, there's my definition for r. So that is going to be a into p plus 2 cos theta. Okay, that's r times the cosine of theta. Okay, so we need to differentiate that, set it to 0, and solve. So to differentiate it, well, I'm actually just going to take the a there, and then I'm going to bring this cosine in. So it's p times the cosine of theta plus 2 times the cosine squared of theta. Okay, so that's my definition of x. So, differentiate it. dx by d theta, the a is going to come out as a multiplicative constant, because it is just a constant. Cos differentiates to negative sign, so that's going to be minus p times the sine of theta. And then this second term, use a little chain rule, and that's going to come to 4 times cos of theta. Then you need to times by the differential of cos of theta, which is minus sine of theta. So we end up with minus 4 times the cosine of theta times the sine of theta. Okay, there's our derivative. We want to set that to be 0. So this implies that either sine of theta is 0. This implies that theta is either 0 or pi. because those are the two values of theta in range, okay, either 0 or pi. Or A is 0, but we know A is not 0, because otherwise it would just be the origin, and that's not what C is. Or we end up with minus P minus 4 times the cosine of theta equals 0. Add P, divide by minus 4, so we end up with the cosine of theta is minus P fourths. Therefore, this must lie between minus 1 and 1. So minus 1 is less than or equal to minus P on 4 is less than or equal to positive 1. Otherwise, I wouldn't have any solutions because it's a cosine function. And if I times it by minus 4, I end up with 4 is greater than or equal to P is greater than or equal to minus 4. Okay, so P therefore must lie between 4 and minus 4. But we are already told that P is bigger than 2. So this then implies that 4 is greater than or equal to P is greater than or equal to, not greater than or equal to, strictly greater than 2. Just check the question though. P lies between 2 and 4 strictly. It doesn't include 4. So we've got solutions here for 4 inclusive. So we have to consider this. When P equals 4, this implies the cosine of theta equals minus 1. This implies theta equals pi. That's an issue because we've already got theta equals pi. So that's not a new point. Okay, so not a new vertical tangent. I should probably put a but over here. Therefore, P can't equal 4 exactly because it wouldn't give 2 lines. We want 4 together. There's 2 there. We need 2 more. So therefore, it must be strictly less than 4. And we can conclude that 2 is less than P is less than 4 as required. Okay, so that's how we go about tackling that question. Okay, John digs a hole in his garden to make a pond. The pond has a uniform cross-section that is modelled by the curve with this equation. So it's the same as R, the definition given in the question, except now we've got A is 20 and P is 3, which is fine because P lies between 2 and 4. Where R is measured in centimetres. The depth of the pool is 90 centimetres. Water flows through a hose pipe into the pond at a rate of 50 litres per minute. Given that the pond is initially empty, determine how long it would take to completely fill the pond with water using the hose pipe. According to the model, give your answer to the nearest minute, and then part D, state a limitation of the model. Okay, so this is 7 marks, so you can expect to do a fair bit of work for this. We need to calculate the volume of the pond. So I'm going to ping onto a new page. Okay, so part D. The cross-sectional area of the pond, which is the shape that we've given, is going to be a half times R squared. So that is A into, oh no, it's numbers now, 20 into 3 plus 2 cos of theta. D theta, so it's half R squared theta, and I want the whole of the curve, so I'm going to go theta values from 0 to 2 pi. But this is a limison, which looks like this. Kind of. My point is it's got a line of symmetry here, so I can actually if I only integrate from 0 to pi, and then I can double it. So I can actually get rid of that half and just go from 0 to pi. So the area is actually the integral from 0 to pi of this integral. So that's going to be 400 into 9 plus 12 cos of theta plus 4 cos squared of theta d theta. Okay, so that's just the cross-sectional area of the pond. Okay, so that's not going to be difficult to integrate, nor is that. This one involves a little bit more thinking. So just recall that cos squared plus sine squared is 1. Also recall that cos squared minus sine squared is cos of 2 theta. And I can use these to find cos squared in terms of cos of 2 theta. So I get 2 cos squared is identical to 1 plus cos of 2 theta. Therefore, cos squared is a half into 1 plus cos of 2 theta. And I can use that in here. So I end up with the area is being equal to 400 times the integral from 0 to pi of 9 plus 12 times the cosine of theta plus, and then 4 times this. So that's 2 into 1 plus the cosine of 2 theta. D theta. Okay, now it becomes a little bit easier to integrate. So I'm going to do 400 times the integral from 0 to pi of 11, okay, 9 plus 2, plus 12 cos of theta, plus 2 cos of 2 theta. And I'm being a little bit lazy with my writing, which is not a problem in your working. I'm just clear what you're doing. Okay, so now that's ready to integrate. So that's going to be 400 into 11 theta. Okay, the 11 is just a constant, so it integrates to 11 theta. That is going to be minus 12 times the sine of theta, and that is going to be minus sine of 2 theta between 0 and pi. Okay, the 2 cancel because the 2 will come out as a divisor from here. That 2's gone. Which means we're going to end up with 400 times 11 pi, and then the rest is 0. So minus 0, minus 0, minus 0, plus 0, plus 0. Okay, so if I plug in pi into here, I get 11 pi, but sine of pi is 0, sine of 2 pi is 0. Plug in 0 in there, that disappears. Sine of 0 is 0, and sine of 2 times 0 is still 0. So all of those are gone except for the first term. So the answer is 4,400 pi. Okay, so that's the cross-sectional area of my pond. I'm told the depth was 90 centimetres, and this is in centimetres. So therefore the volume of the pond, which is 90A, is going to be 90 times 4,400, which is 396,000 pi. Okay, so that's the centimetres cubed. So that's the same as millilitres. Okay, centimetres cubed is a milliliter. 1 centimetre cubed is 1 milliliter. That's a definition you just need to know. So if I divide that by 1,000, that'll give me the number of litres. So that's 396 pi litres. That's how big the pond is. Okay, and let's just check back to the flow rate. So water flows through a hose pipe into the pond at a rate of 50 litres a minute. How long will it take to fill the pond? Give me your answer to the nearest minute. Well, the time is going to equal the volume divided by the rate of flow. You can think of the units. So this is litres divided by litres per minute. That comes out as minutes. So we've got 396 pi divided by 50. And it says to give your answer to the nearest minute. So divided by 1,000, times it by pi, divided by 50, and that gives me 24.88, blah, 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 which is 25 minutes to the nearest minute. Okay, so that's the answer, 25 minutes. Part D was state and limitation of the model. Little 1 markers which can crop up in pure papers. Flow rate is unlikely to be exactly 50 litres per minute for the entire 25 minutes. Or you can talk about the volume as being roughly that, so it's the volume isn't going to be exactly 396 pi litres, because the curve is modelling the pond cross-section or something which will indicate that there will be some deviance from the 25 minutes that we've calculated. Okay. Question number 7. Figure 1 shows a sketch of part of the curve with equation y equals r sine of x, where x is non-negative, and the straight line with equation y equals beta. The line and curve intersect at the points with coordinates alpha, beta. Given that beta is a half log 3, show that alpha is 1 on root 3. Okay, so I'm essentially asked to find that x coordinate, given that beta is a half log 3. So for part A, y equals r sine of x. That implies that sine of y equals x, which is fine because x is non-negative. Plug in y as beta, so I get that sine of a half log 3 equals alpha, okay, because it satisfies the equation x is alpha, y is beta. And now I just use the exponential definition for sine. So therefore alpha is e to the power of that, which is a half log 3, minus e to the minus that, which is minus a half log 3, all over the number 2. Just be careful to show that question, so don't just state the answer. Okay, I know you can plug it into the calculator, but just be careful with these. So that's root 3. Okay, the half will come in as a power using a log law, and then the e and the log will cancel. Minus, do the same thing here, that's going to be 3 to the minus a half, which is 1 over root 3, and that's all divided by 2. Timesing top and bottom of that fraction by root 3, I'll get 3 minus 1 divided by 2 root 3 equals 2 over 2 root 3, which equals 1 on root 3, which is exactly what the question says alpha should be. Okay, so alpha is 1 on root 3, and we've shown that. Okay, and showing this working proves to the examiner that you've actually carried out the calculation, as opposed to just stating the answer. The finite region R, which is this region here, bounded by the curve y equals beta and the y-axis, is rotated around the y-axis. The region R, the region R is rotated 2 pi radians around the y-axis, so the whole thing gets spun around the y-axis. Use calculus to find the exact volume of the solid generated. Okay, so this is for 6 marks. So this is a volume of revolution around the y-axis, so we need to go from y values of 0 to beta, and it's times pi x squared. So the volume, part B, is going to equal pi times the integral from my 2 y limits, which was y is 0 to y is beta, which was a half log 3, of x squared, which is sine of y squared, okay, because x equals sine y, and that's with respect to y, because they're y limits. Okay, so that's the integral I'm carrying out. You can use hyperbolic identities here. I think it's probably slightly easier to go into exponential form, but it really doesn't matter which route you take. You just need to make sure that your answer will be exact when you're finished. So sine is e to the whatever it is minus e to the minus whatever it is over 2. So sine squared then is the square of that, which is e to the 2 minus 2 plus e to the minus 2 over 4. Okay, so that's what sine squared will equal. I mean, it's just squaring this fraction. So the contents of this is y, so my capital X over here in my identity calculation is just y. So it's the integral from 0 to a half log 3 of e to the 2y minus 2 plus e to the minus 2y, all divided by 4 dy. And now I can evaluate all parts of that integral. So e to the 2y over 4, that's going to integrate to e to the 2y over 8, because I'm dividing by the 2. The minus a half in the middle is going to go to minus y on 2. And then this over here, again, the minus 2 is going to come down as a divisor. So that's minus e to the minus 2y on 8. And that is between 0 and a half log 3. Okay, now plug in the upper limit. Again, the pi can just sit there. He's not doing any harm. E to the 2y. Okay, so times that by 2. That's obviously going to cancel with the half. So it's e to the log 3, which is just 3. Minus log 3 on 4. Because the half there and the half there will times to give a quarter. And then again, the minus 2 will cancel with the half to make a minus 1. That minus 1 will come in as a power. So that is actually a third over 8. Plug in 0. That goes to an eighth. That is 0. And then that will go to an eighth as well. Okay, but those two do cancel out, so that's not a problem. Just be careful with plugging in 0 because it's not always 0. Okay. So it's just a case of just neatening this up. I'm going to pull an 8 out, just so I don't have any fractions kicking around. Oh no, I need to pull a 24th out even. Apologies. So if I pull a 24th out, I've got 6 here, and then minus 1 there, so that's 5. And then I will have minus 6 log 3 there. And I believe that's my answer. Let's just check that that is a positive number. 6 log 3. It is not a positive number. Okay, that is concerning because you would expect it to be a positive number. 24 divided by 4 is definitely 6, yeah, okay. Okay, let's see where I've gone wrong. Oh, it's 9 minus 1. So when I pull out the 24th from here, that's going to be 3 times 3, which is 9, minus the 1 from here. So that should be an 8. Okay, let's try that. 8 minus 6 log 3. Okay, that's better. Right, now to check my actual answer. Okay, I know it's... I don't know it's definitely right, but I knew the other one definitely wasn't because it was negative, and that can't be right. So pi times the integral of shine, which is in the options. So shine of x squared between 0 and a half log 3. So that's what the actual number is as a decimal, is 0.184349. Okay, and this number here, pi on 24 times 8 minus 6 log 3. Good, that comes out as the same number. So I wrote the number down up here from the integral. The calculator gave me that number as the integral, and the calculator just gave me the same number from my calculation here. So I can confirm that I'm happy with that. I will pull out, now that I can see there's a 2 across the coefficients here, I'm going to pull out a 2, so that's pi on 12 into 4 minus 3 log 3. And I'm happy that that is indeed the correct answer. And that was 6 marks. Okay, so all of that there was 6 marks. So it's not too bad if you know what you're doing. Okay, question 8, which I think is the penultimate question in this paper. Yep. The point P is one vertex of a regular pentagon in an Argand diagram. The centre of the pentagon is the origin. Given that P represents the complex number 6 plus 6i, determine the complex numbers that represent the other vertices of the pentagon, giving your answer in the form re to the I theta. Okay, so 8 part I. Quick sketch of the Argand diagram just to show you exactly what's going on. I've got 6 plus 6i, which is over here somewhere. There's my point P. And that is 1 point of a pentagon, regular pentagon, centered on O. So the other coordinates will be maybe 1 over there somewhere, 1 over here somewhere, 1 down here somewhere, and 1 over here somewhere. Not a great sketch, but that is a regular pentagon. There's my real axis, and there's my imaginary axis. And because that's a regular pentagon, all of these angles that are subtended at the centre have to be equal. So they must be 2 pi on 5, because there are 5 altogether, and they must sum to 2 pi because it's a full circle. So all of those are 2 pi on 5. So for questions like these, I need the modulus of p, which is going to equal the modulus of all the others because it is centred on 0. And I need the argument of p, which is that angle there. And then I need to add multiples of 2 pi on 5 to that to get the others. Okay, so that you don't have to do a diagram. I just wanted to illustrate how we go about solving these problems. So the modulus of p, so 6 plus 6i, that is equal to 6 root 2. Therefore, all of these moduli will be 6 root 2. The argument of 6 plus 6i is pi on 4. And hopefully you can see that from the diagram. If I've gone 6 in the real direction and 6 in the imaginary direction, then that angle is going to be arctan of 6 divided by 6, which is pi on 4, or 45 degrees. And from that I can calculate the others. So that implies that my other theta values are going to be multiples of pi on 4. So pi on 4 plus 2 pi over 5 is 13 pi on 20. If I add another 2 pi to that, I think that pushes me over the top. It does, it's 21 pi on 20. So to bring that back into between minus pi and pi, I subtract 2 pi from it. So it's minus 19 pi on 20. If I subtract 2 pi, I get minus 3 pi on 20, and the other one is if I subtract 4, minus 11 pi on 20. So those are my other 4 arguments, and all of them will have the same modulus. So once the answers in the form re to the I theta, therefore I'm just going to list them out. So 6 root 2 e to the 13 pi I on 20, 6 root 2 e to the minus 3 pi I on 20, 6 root 2 e to the minus 11 pi I on 20, and 6 root 2 e to the minus 19 pi I on 20. Those are my 4 other vertices, which is asked for the other vertices of the pentagon in that form. So that's it. Part 2. On a single Argand diagram, shade the region R which satisfies both of those, and then determine the exact area of R, giving your answer in its simplest form. Okay. So we need to sketch an Argand diagram. So let's pop that on. There's my real axis, and there's my imaginary axis. The first one, I'm told the modulus of z minus 2i is less than or equal to 2. So this is a circle, because it's just got a modulus there, so it's a circle, centred on 2i with a radius of 2. Doesn't need to be amazing. Okay, so it's everything inside that circle. That's got a centre of 2i, goes up to 4i, and then comes down to the number 0 on my Argand diagram. And then this one is an it's 2 infinite half lines. So I'm told that the argument of z lies between pi on 4 and pi on 3. So they're both going to be infinite half lines from the number 0, one with an argument of pi on 4, one with an argument of pi on 3. So pi on 4 is a 45 degree angle, which does that. And pi on 3 is a 60 degree angle, so it does something like that. So that's the locus argument of z equals pi on 4, and the argument of z equals pi on 3. And then this circle has equation modulus of z minus 2i equals 2. So that's the locus, that's the boundaries of my region. And just check what it wants. It wants the argument to be in between pi on 4 and pi on 3, and it wants the modulus of that to be less than or equal to 2. So therefore, this is my region R, because that is the region that's in between those two infinite half lines and lies inside the circle. Part B, determine the exact area of R, giving your answer in its simplest form. Okay, so this was part 2A. Part 2B, we want to calculate the area of that. It's a little bit messy because this point is not from the centre of the circle, so it's not as obvious to consider the area. I think maybe putting it into polar form might be good, because then it's got the limits of pi on 4 and pi on 3 already. So I could consider this curve as being a rhodonia with one petal. So if I consider R is equal to 4 sine of theta, I think that would express this. Let me just check. So when theta is 0, R is 0, so it starts at the origin. As theta increases, it's sine. When it goes up to pi on 2, it's at 4, and then comes back down to when theta is pi, when it's 0 again. Yep, so that's a rhodonia, and that's in the right orientation. So that's the polar equation of that curve, and therefore the area is going to be equal to a half times the integral from my two theta limits, which is pi on 4 and pi on 3, of r squared, which is 16 sine squared of theta d theta. Okay, don't forget from earlier, cos squared plus sine squared is 1, cos squared minus sine squared is cos of 2 theta. Subtract them this time, so I get 2 sine squared is identical to 1 minus cos of 2 theta. So therefore sine squared is 1 minus cos of 2 theta over 2. And I can use that in here to allow me to integrate sine squared. So the area of my shaded region is a half times 16 times a half, which is 4, times the integral from pi on 4 to pi on 3 of 1 minus cos of 2 theta d theta. And evaluate that integral. So that's 4 into theta minus, minus because it's an integral, a half times sine of 2 theta between pi on 4 and pi on 3. Okay, plug all that through. 4 times pi on 3 minus pi on 4. Okay, so that's those two in the first there. Minus a half times sine of 2 pi on 3. Plus a half times sine of 2 times pi on 4, which is pi on 2. That last one goes to 0 anyway, because sine of pi on 2 is... Oh no, sine of pi on 2 is 1. Ignore that. That's not 0 at all. Okay, so what we're going to get is pi on 3 minus pi on 4. That's 4 twelfths minus 3 twelfths is 1 twelfth. But it's times up by 4, so that's a third. So it's pi on 3. Sine of 2 pi on 3 is root 3 on 2 times a half, and then times up by 4. So that's just root 3, so minus root 3. And then this number here, sine of pi on 2, is 1 times a half times 4. Okay, so I get pi on 3 minus root 3 plus 2. And we can, of course, check that by plugging in this original integral. So a half times the integral of 16 times sine of x squared between pi on 4 and pi on 3 is that number, 1.315147, blah, blah, blah. And this number here is 2 plus pi on 3 minus root 3. It's the same number, which is very reassuring. There are other ways you can do it. You can look at it geometrically, but it isn't easy geometrically because this point isn't the centre. You have to faff around a little bit. Okay, for example, join that point up there, find the area of that triangle, and that sector, and then you need to take away this cap as well, which is another sector minus a triangle. So you're just faffing around a lot with the geometrics of it. It's possible, but I do think using polar coordinates was the best way to go there. Okay, final question, question number 9. Given that the modulus of z is less than 1, write down the sum of this infinite series. Well, this is just geometric, because you're timesing by z each time. So therefore, it's a geometric series. With a is 1, that's the first term. R is z, and the number of terms is infinite. Okay, told it's infinite series. So the sum then, sum to infinity, is a over 1 minus r, which you're given in the formula book. So it's 1 over 1 minus z. And that's it. That's the answer. Part B. Given that z is this thing, which is a half into cos of theta plus I sine of theta, use the answer to part A and De Morve's theorem, or otherwise, to prove this is true. Okay, so this looks like a C plus IS thing, doesn't it? But there's no C plus IS written anywhere. So let's define C and S, and then let's work through that theory. So I'm going to say let C equal 1 plus a half cos of theta plus a quarter cos of 2 theta, and so on. And let S equal a half sine of theta plus a quarter sine 2 theta, and so on. And I've put a 1 up here in the cosine because there's a 1 in the original series up there. And also there's a 1 here when I get to it in a minute. So I've included the 1, and that's when theta is 0, essentially. You get 1 over 2 to the 0, which is 1, times cos of 0, which is 1. And then here you get 1 over 1 times sine of 0, which is 0. So there is a 0 term there. Okay, so those are the two definitions that we want, C and S. So C plus IS, well, that's just going to be the sum of these, isn't it? So 1 plus 0 is 1, plus a half times cos of theta plus I times sine of theta, plus a quarter times cos of 2 theta plus I times sine of 2 theta, and so on. Which is exactly what we've got at the top. It is 1 plus z squared plus z cubed plus dot dot dot, and so on. Okay, because we're told z is a half cos of theta plus I sine of theta. So using De Morve's theorem, that's z squared. Okay, the half squared is a quarter. Cos of theta plus I sine of theta squared is cos of 2 theta plus I sine of 2 theta, which is application of De Morve's. And we've already said that equals 1 over z. Sorry, 1 over 1 minus z. So that equals 1 over 1 minus z, which is 1 minus a half e to the I theta under 1. I'm going to times top and bottom of that by 2, just to get rid of the fractions in fractions. And I'm also going to times it by e to the minus I theta. Oh, actually, no, I'm going to come back to that. It's going to times it by 2 to start with. So we end up with 2 divided by 2 minus e to the I theta. And now I'm going to times the top and bottom by the conjugate of the bottom to make it real, which is 2 minus e to the minus I theta divided by 2 minus e to the minus I theta. Okay. Common mistake here is to say the conjugate is 2 plus e to the I theta, which is not correct. By definition, the conjugate has the opposite sign of the coefficient of I. So it's the coefficient of I you need to change. At the top will then become 4 minus 2e to the minus I theta. The bottom will become 4 minus 2e to the minus I theta minus 2e to the I theta. I'll come back to that in a minute. And then those two cancel to give a plus 1. So that's 4 minus 2e to the minus I theta all over 1 plus 4, which is 5. And then that is cos of theta plus I times sine of theta. And then this minus bit here is minus cos of theta minus I times sine of minus theta. There should be a minus there. But those two will cancel, so the sines will cancel out, and we're left with these two cosines adding together. So that actually will become, oh, there should be a plus in there as well. Yeah, plus there. So that'll actually become 2 times the cosine of theta. So therefore that's minus 4 times the cosine of theta. Okay, so that's what C plus IS equals. We're asked to just consider S. Okay, that's the definition of S down here. Half sine theta plus a quarter sine 2 theta, etc. So S is the imaginary part of that. So S is the imaginary part of C plus IS, which is the imaginary part of 2 minus e to the minus I theta. I think, check that. Sorry, it's 4 minus 2. The imaginary part of 4 minus 2e to the minus I theta, and that's all divided by 5 minus 4 cos of theta. That number 4 is real, so it's just the imaginary part of this, which is equal to minus 2 times, and the imaginary part is sine of minus theta, 5 minus 4 cos of theta. Sine of minus theta is minus sine of theta, times by minus 2. We'll get 2 sine of theta divided by 5 minus 4 cos of theta. I believe is what it wants. Yeah, 2 sine of theta divided by 5 minus 4 cos theta. Part 2, show that the sum of infinite series 1 plus z squared plus z cubed, etc. cannot be purely imaginary, giving a reason for your answer. So purely imaginary that implies the real part equals 0. That's what it means to be purely imaginary. So the real part of C plus IS is equal to the real part of 4 minus 2e to the minus I theta all over 5 minus 4 cos of theta. Four is real, minus 2 times the real part of that, which is cos of minus theta, all divided by 5 minus 4 cos of theta. That's the real part. We want that to be 0. This implies then that 4 will equal 2 times the cosine of theta. This implies the cosine of theta equals 2. Well, that's not possible for theta is real. Therefore, the real part is never 0. Therefore, the sum is never purely imaginary. Okay, and that's it. Hopefully you found that useful. Please make sure you check your answers to those. I've sent those back to you online. If you have any further questions, please don't hesitate to email me or just ask me in class. Hopefully you found that useful. Thank you very much for watching.